Good morning. Now we will solve the problems that is 7, 8, 9, which are from assignment number 11. So we have given this data which is related with your industrial building, spacing of truss 5, spacing of purlins 2, wind speed 45, weight of sheet 110 Newton per meter square, and dead load of purlin 110 Newton per meter. Calculate the value of bending moment due to normal load. So now we have weight of galvanized sheet 110 Newton per meter square. Purlin is given 110 Newton per meter. So to total dead load, now we are multiplying it by spacing of purlin. So they have assumed this load is acting on inclined area. Therefore, they have multiplied by spacing of purlin. So 110 into 2 plus 110, 330 Newton per meter. Total dead load, normal to roof. We have this load actually, we have wind load. So that load act perpendicular to this. And therefore we have two components. One is normal, another is perpendicular. So normal we have to consider that is, so angle, we have this angle theta. And therefore that will be cos theta. So 285.79 Newton per meter. Wind speed is given 45. We know design wind pressure 0.6 Vz square. And we will get this value 0.6 into 45 square. 1112 Newton per meter square. Again acts on inclined area. So multiplied by spacing of purlin gives value Newton per meter. Here also this is Newton per meter. And as we are multiplying it by 2, so this also we have Newton per meter. So 2424 Newton per meter. Then total load we have. So add, we have number 1, that is, this is first value which is due to sheet and purlin, and this is second value. So we will add these two values, we will get total load. Then we have mu w 1.5 because we have to make ultimate. So when we will multiply 1.5, this will be w. So we have this value 27. So this we do not consider over here. So we have this as 1.5 WL square by 10. And then we will substitute value L we have, that is spacing of truss. And that is given, or we have span of purlin, so 5 meter. And from this we will get value of mu 10.16 into 10 raised to 6 Newton millimeters. So it will be 10.16 kilonewton meter. And then we have 10.16 goes to 10.2 kilonewton meter. Option we have D. Then next we have determine the plastic section modulus of ISMB 450 and about both axes, and data we have given. Now we have to keep in mind here, when we will go with plastic section modulus, we have to use plastic neutral axis, and plastic neutral axis always divide your area equally into two parts. And then one part will be in compression, another will be tension. And then we will go with this, the relevant properties we have given. And now we will go with first. So we will consider data that will be, sorry, we will consider plastic neutral axis at center. So we have this as plastic neutral axis. Now this value we have given, TF is 17.4. Then we have this value 150. TW we have given 9.4. So now this is also 17.4. So if we will subtract this thickness of flanges, that is from total depth. So we have 450 minus 2 into 17.4. This value comes 415.2. So this total value 415.2. So now this will be half of this value. So if I will consider this value, so we have divided by 2. So divide by 2, 207.6. So this total is your 225. Because that plastic neutral axis, when symmetrical, we have plastic neutral axis and elastic neutral axis along the same line. So now we are interested, we have twice of this because we symmetrical. So we have to find ZP plastic, half of this and multiply it by 2. So this is about ZZ axis. So now we have, so you can see this 2 times. So 2 already I mentioned. So 150 into 17.4. And then we have to find this value that is from center of this, center of its own centroid to the plastic neutral axis. So we are interested with this distance. So what will happen? So we know this distance is 17.4 divided by 2. And then we have 225 minus 17.4 by 2. So this is area multiply x bar. So we have AC into x bars, AC1 into x bar C1. Plus, now we have to consider this 2 times, so this consider tension also here. Then we have next, that is for this portion, which is 207. Now it's directly half of 207.6. 207.6 upon 2. So area we have 207.6 into 9.4 and into 207.6, and it comes value 1534.21 centimeter cube. That is ZP along Z axis. Then we will go with Y axis. Now in Y axis actually we have this. My plastic neutral axis and my centroid of each area are same. So we have plastic neutral axis. And then we have to consider twice of all these values. So this will be twice plus twice of this, means we have total 4 times. And then we have twice of these values. Now what will be this value? So we have, this will be 9.4 by 2 and it comes 4.7. And then we can find plastic neutral axis along this line. So we have this value now 75. And from its centroid, we have this distance that is 75 by 2, which is x bar. So now we will go one by one, 4 times. I already mentioned. So we have, this is 1, 2, we have 3, and then we have 4 times. So 4 times 75 into 17.4. We have thickness of flange as 17.4 into 75 by 2. It will act at center. Plus 2 times of web. So 2 into, so this is 9.4 by 2, 4.7 into this distance already we know, which is 415.2. Same we have considered over. And then we have CG of this. So what distance we will get x bar? So this will be 4.7 by 2 and 4.7 by 2. So if I will put it as in terms of 9.4, so this comes 9.4 by 4. This 2 and this 2. And therefore it will be 9.4 by 4. And then we will get ZPY. So actually this will be ZPY. So ZPY equal to, and then we have this value 204.92. So 204.92 and 1534.21. So we have an option for this. So 204 and 1534. So we have option for this is option A. So option A we have 1534.204. So we can see this 1534 and 204. And then last we have, in the design of angle purlin section subjected to UDL, the maximum bending moment is calculated. So this is given WL square by 10. So WL square by 10. So we have option that is B. So likewise, we have to solve the problems which are related with your assignment number 11. Now we will stop here only. The remaining part we will see in the next examination. Thank you.